Hi everyone, we're doing another lesson today for Calculus 12 on Chapter 3. So we're doing 3.5 related rates, and I'm just going to quickly run through this, but you don't necessarily need to write this down, it's your choice. But when we're looking at related rates, again, this is just applications of derivatives. So in the first part it says differentiating with respect to time. So that's significant, I'll underline that. We are given the rate of change of one quantity, and then we're asked to find the rate of change of a related quantity. So I'll show you with examples to help it make sense. We do this by finding an equation that relates to the two quantities and differentiate both sides with respect to time. So there's the main points to look for, but let's dive right into an example so you can see exactly what it is I'm talking about. In the first example, it says air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the radius of the balloon is increasing when the diameter is 20 centimeters. Okay, so this helps us to kind of see what these points we're talking about. It says we are given the rate of change of one quantity and asked to find the rate of change of a related quantity. So to put things into perspective, let's take a look at this part, a rate of 5 centimeters cubed per minute. So our V prime of t is equal to 5, since the rate of change is just the derivative. We know that, right? And actually, let's sort of look at this as well. We're dealing with a spherical balloon. So a formula wasn't given to us. It's assumed that you know this. In case you've forgotten, I have no problem with reminding you or giving you this, even if it's on a quiz or test or something. But I think as we work with this, you're going to refresh your memory and it'll probably come back to you. But remember that the volume of a sphere is 4/3 pi r cubed. So good to write that down and keep that in mind, because that's what we're dealing with. That's what we're working with here. And so when we look at this, it says determine the rate at which the radius of the balloon is increasing. So where the radius of the balloon is increasing when the diameter is 20 centimeters. Okay, so if the diameter equals, that looks like a P, let's change that, diameter equals 20 centimeters, then we know that that means the radius must be 10 centimeters. So just basically going through and picking out the information that is given to us and organizing it, and then using that to help figure out what it is that we're trying to find here. Okay, so notice that we're dealing with everything with respect to time. It says that right here. So it's helpful to know that, or to think of that, or to keep that in mind as we're working our way through this. So we want to rewrite this to say V of t is equal to 4/3 pi r cubed. And another way that we can write r with respect to time is I could say that this is r of t in function notation, which is equal to 10 centimeters as we were given in the question. So, I mean, this and this are the same thing, just again, sort of tying it all together and putting it in terms of this. And then notice that this is the same thing as this. So I can substitute that into here. I can rewrite this to say that my V of t is equal to 4/3 pi, and instead of r cubed, I'm going to do this so that we can tie it all together and look at the overall big picture of what's going on. Okay, so again, kind of like what I wrote there, technically this and this are exactly the same thing. So there's not really any difference between them, just that I've rewritten it to put it all with respect to time. So that's all that I'm doing with that. And notice that in the last section of chapter 2, you learned how to work with these composite functions and put things together to be able to look at it in terms of this. Okay, so then we wanted v prime of t. So that means we want to take the derivative of this whole thing. So when we take the derivative of this whole thing, to put this into perspective, that 3 would come down. So my 3's are going to cancel here. So I'd have 4 pi. So again, so that you can kind of see or make sense of this, it's like that and that end up canceling when we do the power rule, right? So we're left with 4 pi. And then we have this part, the r of t, and that's all going to be squared because we took 1 off the top here, as we know with the power rule. But then I'd also have to have r prime of t because of the chain rule. So you get to see how we're sort of putting everything together within one question. So we get to sort of practice all the skills that we picked up in chapter 2. Okay, so working our way through all of this, let's sort of start to put this together. We know from up here that our v prime of t is equal to 5. So I can substitute in 5 here because we already knew the value of it. So that will help us to be able to work our way through this. Equals 4 pi. And then we also knew that r of t from right here is equal to 10. Or sorry, I guess I should use that one instead, but same thing. So that is equal to 10 here. And then, you know me, the color coding is the hardest part, but I can do that. Technically, that should probably be like that. Okay, and then times r prime of t. Times r prime of t. Okay, so if we take a look at this, just to remind you, because it's easy to get lost in all this stuff, all the calculations, and forget what you're looking for, determine the rate at which the radius of the balloon is increasing when the diameter is 20. So that would be r prime of t. That's what we're looking for. So since that's the only variable we have left here, we can simply simplify this. So 5 equals, when we do this, we'd get 100 times 4. So I have 400 pi, and then r prime of t. And we can divide 5 by 400 pi. So when we simplify this all, I'd get 1 over 80 pi because 5 goes into 400. And I guess we should put the units would be centimeters per minute. And that is our r prime of t, or the rate at which the radius is changing with respect to time when the diameter is 20 centimeters, because that's what we plugged in there. So after all of that, this is the rate that we end up getting. And trying to show you all of it, but I realize that the screen sometimes cuts off the bottom. So I hope that you're able to see all of that and make sense of it, but the key idea or concept behind this is you figure out which information you are given, you figure out right at the start what it is you're looking for, and try to look for similarities between the two. So putting them both in terms of time is what I'm referring to there. So that's sort of the pattern or what we're looking for as we're working our way through these. Okay, so let's try one more. We have a 15-foot ladder that is resting against the wall. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 feet per second. How fast is the top of the ladder moving up the wall? Oh, I guess this is cut off. 12 seconds after we start pushing. After we start pushing. After the start, I'm going to say. There we go. That works. Okay, so you don't have to do this, but I feel like this is often helpful to draw a diagram so we can see what is happening and make sense of the information and basically just use it to organize and figure things out here. So we know the ladder is 15 feet. So this is the ladder here, so I'm going to say that's 15 feet. Okay, so that's good. It's resting against the wall, so this would be my wall here. The bottom is initially 10 feet away from the wall. So there's the bottom of the ladder, and if it's 10 feet away, so then that's my 10 feet, at the start anyways. Okay, so, and then it says it's being pushed towards the wall at a rate of, so let me do this, being pushed towards the wall at a rate of 1/4 feet per second. So, if this is x, I'm going to call this x prime. That would be like going in that direction. So it would be being pushed towards the wall at a rate of 1/4 feet per second. So do you see that it would be, I'm going to make it negative 1/4, and I want to talk about that a little bit. I'm making it negative 1/4 because as we push it towards the wall, we're actually decreasing the value of x. So that's the reason why I've put this negative in front, which is similar to the stuff that we did last day actually, when we looked at negative time, and we talked a little bit about that as well. Okay, and then how fast is the top of the ladder moving up the wall 12 seconds after the start? Okay, so we also have this going on here. How fast is the top of the ladder moving up the wall? So that would be like right here. So we're looking for y prime. We're told x prime, we're told the diagonal or the hypotenuse, we're told the bottom. So we can start to work with this information and make sense of what's going on here. So I also want to label this, and I want to call it, and now I'm wishing I had drawn this bigger, but I'm going to sort of go down here. We're going to call this, x of t. So this is meaning the distance or that length of the bottom with respect to time. And I'm going to call the other one over here y of t. Again, like the whole distance top to bottom with respect to time. So you can start to see how this all relates to one another. But the key idea in the last example and in this one, and actually in most of the stuff we do, is that you're looking for similarities. You're looking for the thing that ties everything together, and it's time. So x prime was negative because we're making the distance smaller, but notice that y prime is going to be positive because it's actually increasing as we push the ladder up. So that is the thing that we are looking for. So I'm going to underline it in pink because that's the part there that I've done in pink, so you can sort of start to put it together and make sense of it. Okay, so we're looking for relationships between x and y. Clearly this is a right angle triangle, the shape that it forms. So we can say x squared plus y squared is going to be equal to 15 squared. We know that using Pythagorean theorem. So we can say x squared plus y squared equals 225. Okay, so there's our first equation, first relationship. So we can look at that, and then we can also differentiate both of the sides. When we do that, we would get 2x, and I'm going to put in here x prime, because I know we haven't done this or seen this before, but we are working with x prime. So we are putting in that x prime there because we have that information. We're looking at related rates. So we're looking at the rate of the bottom and the top. So we do include that in our differentiation. Plus we would do here 2y times y prime. Oh, look at that. I told you the hardest part is keeping the color straight. So let me do that in green or in pink so you can see what it coordinates with. And then on the right side, the derivative of a constant we know is always just equal to 0. Okay, so then that's a part of what we were working with, so that's all good. And I'm going to put this in a little box because this is going to be pretty significant coming up here. Okay, we can figure out x and y. So down here, maybe I do, no, I don't know. I'm going to put x here. So we know that distance is equal to rate times time. Or you could look at it the other way, like rate or speed is equal to distance over time. So we've just rearranged that equation. So knowing that, we know that the rate would be basically this guy here. So I can plug in 1/4, because I don't need the negative part. I'm not looking at that. I want to figure out what the value actually is. And then we were told here that we're looking for it 12 seconds after the start. So my time at that point would be 12. So then working my way through this, I would see that the distance at that point, the x value, is going to be 3 feet. Okay, so the end of the ladder has to be pushed in 3 feet, meaning like in this direction, it would be pushed in 3 feet. So if it's pushed in 3 feet, then we must have 7 feet for x. I'm going to get rid of this because we don't need it. So to put this into perspective, up here in the diagram, we started with 10 feet, and through our calculation here, we found that the rate times time ended up giving us 3 feet, so it must have moved in 3 feet. I guess I could have done negative because we are taking off that 3 feet. So we end up with 7 feet for our x value. So I'm going to put that in the box so we can use it. And then moving on, let's take a look at, so that was our x there. Let's take a look at our y, which again, I should do in pink to keep it consistent. We can reuse Pythagorean theorem. So in our Pythagorean theorem equation right here, we can plug in what we just found. So we know that y would be equal to the root of 225 minus x squared. So again, this is just me taking this Pythagorean theorem, x squared plus y squared equals 225, isolating it, isolating the y and filling it in this way. So in order to get my y value, I would have 225, and I'll color code it again, minus this value we just found here, which is our 7 squared. Oh, I was supposed to do that in blue. There we go. So we end up with root 176 for our y value. So we now have all the stuff that we need. I'm going to try to bring this back so you can see it all, and I'll carry on maybe up here. And I realize you may not be able to see the bottom, but I will rewrite it and bring it back up in just a second. But in our equation, maybe I should say like up here, we're going to take this equation that we had, and we're going to start to plug things in because we actually have all the information that we need, and we can use that to solve for y prime, which is what we're looking for. So we have 2 times our x value, which we found here in blue to be 7, times our x prime, which we know was negative 1/4. Okay, I'm going to move this aside so you can see this part clearly. And then we have plus, whoops, wrong color, plus 2 times my y value, and we just found the y value down here to be root 176. That's the thing we just finished calculating. Times y prime equals 0. So we worked our way through and found all of the missing components, and we plugged them back into that differentiated equation. And now we can see that we just have this one little y prime that we need to get by itself to isolate to figure out what the answer is. So when we clean this all up and move it aside, well, actually right here, I will clean it up a bit. Negative 7 over 2 plus 2 root 176 y prime equals 0. So 2 root 176 times y prime equals positive 7 over 2 when I move this guy over. So my y prime is just equal to 7 over 4 root 176, which is approximately 0.1319 feet per second. We would write this in a sentence. We're not going to because this is getting pretty long, but go back and read it over and double check that you understand what it is we just found. So, how fast is the top of the ladder moving up the wall? 12 seconds after the start? Well, it's moving up the wall at a rate of 0.139 feet per second at that time, 12 seconds after the start. So, I hope that you found that helpful. Page 145, numbers 1 to 7, 10, and 11 is the suggested work that I'm giving you. And that's it.